Okay, but does Tim have one as well, and Bruno, or
You will have to share.
but maybe okay. Yes, I'm starting, right? So
Yeah, you are starting.
exactly.
That's why I'm starting with you.
Is it
Is it where?
this way, right?
Yeah,
Is it? I mean, feels right.
It looks professional.
Looks professional. Yeah.
Yeah, I have one company who experimented
can you
with.
try to say something?
Testing. Oh yes, it works. Lovely. Nice.
And you can move. So we can start.
Oh, okay. All right. We'll talk later. Yeah, no worries. Thanks. Nice meeting you, mate. Yeah.
We are recording.
Yeah.
You can move with the arrow.
Okay. Nice. That's good enough for me.
Yeah.
I'll just grab a drink.
Yeah.
And then I'll yeah. All right. Beautiful. Hello. Does this work? Yes, it does. I think we will begin now. So if you could take your seats, that would be lovely. It's very dispersed, you know. It's, but it's nice. I don't mind. I'll just put this on mute because my boss will ping me. Yes, thank you for coming here, and thank you Funnel for hosting us here. This actually looks very, very nice. This venue, it looks very, very professional. My name is Armin Catovic. I'm head of AI at Aloi, a legal tech company, but I'm also vice chair at Stockholm AI, which is a meetup community. So we try to run or help companies and organizations sort of organize these informative events that you see here. What I'll just do is actually put this here because the first thing I wanted to ask is how many of you are members of Stockholm AI? So eyeballing at 50%, I would say. So if you're not a member, what you do is you take your phone, take the camera out, and you point at the QR code, and it's free, right? So there's no cost involved. You fill in a simple form, and you get access to Slack, where we discuss a lot of interesting things, and you get newsletters, and you get preference when we set up these events as well. So that's very nice. So I'll leave that for now. I'll just talk a little bit about what we do. We organize events like these. We also have mentorship program as well, where we pair up young, not necessarily young, let's say just people that are interested in getting started with AI. Whether it's from technical perspective, whether it's from business, maybe they have an idea, they want to solidify that into some kind of a proper business or a startup. Maybe they just want to learn about AI just to get a feeling for it so they can kind of feed that back into their company where they work. So we have a mentorship program. We try to have some more kind of technical, very technical sessions as well, like hands-on kind of hackathons and little workshops as well. So that's what we do. And we do it free of charge. And also we do it with the help of companies like Funnel as well that provide this beautiful food over there and the drinks. We do have some sponsors as well that give us a little bit of money or provide venues for us. In this case, Funnel is providing the venue and the food, which is amazing. In other cases, we either do it through our sponsors, so we do it ourselves with their finances. So we'd like to thank them as well for that. But I will hand over now to Bruno, who is going to talk about Funnel.
Thank you. I think, where is it? Here. Almost there. All right. I got a couple questions earlier about who we are, what we do. So I'll start with that. I'm Bruno. I work here at Funnel, been here a while, and my current role is AI product director. That means I work on AI projects with Peter over there and Ola, who's not here today, and Andre. And we work on both internal AI projects as well as customer-facing AI software. Now, Funnel, we have about 2,500 customers, an office here in Stockholm, one in Boston and in Sydney, and we're more than 300 people. And just to give you a sense of what we do, so we build a marketing intelligence platform used by lots of brands. So we have brands, retail, service companies, digital agencies, so lots of different customers. The big thing here is we're a B2B company, so we sell software to other companies. And the basic idea of a platform is what we call the marketing intelligence platform. There's the basic idea, and where we started is unifying marketing data for companies. If you run a business, you might have ads. You might run ads on Google and on Facebook and in lots of different countries and on many more platforms, and you try and want to make sense of what the hell's going on. And we started to solve that problem by connecting to all these platforms and bringing all that data together. So that's the data integration part. Now, since then, what we do has evolved a lot. So we now do media planning as well. We'll do marketing reporting, so you can actually report on the data in our platform. And we'll hear from Tim shortly. We also do marketing measurement, so taking your data a step further and really generate insights from it. And then finally, we also do data activation. So for those of you who work in the marketing space, you often want to send signals back to the advertising platforms, and that's something that we can help you with. So that's a basic idea of our platform. If you have questions about it, talk to anyone with a Funnel t-shirt. Now, briefly want to touch on AI at Funnel, mention a couple of things. We are working with AI in different forms. So we've been running projects on improving internal productivity. We're working on LLM-based features as well. And then we have a fantastic data science team in Hamburg that does a lot of traditional ML and more cutting edge things. And we'll hear from Tim shortly. And one thing that I really enjoy about working here is like we have access to all the fun tools. So whether it's Cursor, Lovable, ChatGPT, Gemini, etc. One thing I enjoy about coming to work is there's really no holds barred. We get to try stuff out and work with all this cool new tech. And since we're on that topic, some of you asked about this. We are hiring. Where's our talent team? Yes. So if you're interested, talk to them or go to jobs@funnel.io. Yeah, we'd love to hear from you. We have a bunch of open positions at the moment. Yeah, and that was it for the short intro on Funnel. And now we're here from Tim, who's going to talk about AI for analytics and market insights. And Tim, you're the head of our measurement and data science team at Funnel. So give it up for Tim.
Thank you very much, Bruno. Yeah. That one. Perfect. Yeah. Welcome everyone to the funnel office. My name is Tim. I'm in charge of the advanced measurement rectangle that Bruno just showed, based over in Hamburg. So really sorry, Armin, that I'm not a member of Stockholm AI, but I just don't live in Stockholm. All right, I'm going to do that afterwards. So cool. So today I'm going to talk a little bit about marketing mix modeling at scale, MMM, marketing mix modeling. So what is this actually all about? Marketing mix modeling, it's part of the answer. How can you solve the attribution problem? Does anyone know here what we mean by the attribution problem? No? Okay, perfect. So essentially, what we mean by that is we're trying to figure out what part of our marketing had what impact. So you might have heard about this quote, half of the money I spend on advertising is wasted. I just don't know which half. And we are trying to reduce that to a third or fourth, maybe 40% if we're lucky. So part of the answer to that puzzle is actually marketing mix modeling. Marketing mix modeling, it is I would say rather ancient technique that already existed back in the 80s or 60s, whatever. I wasn't born. It existed back in the day. It's normally built on top of or based on multiple regression, OLS, linear regression, whatever. But actually, what you're trying to do is you are trying to build a relationship between marketing investments, other outcomes, or other inputs like pricing, promotion, whatever, and sales. So it sounds pretty straightforward. Who of you are data scientists? All right, a few, right? So it sounds pretty easy actually when you come from a world where you fit like trillion-dollar parameter neural networks. Rest assured, it's not. It's actually pretty fucking difficult. So why is marketing mix modeling so difficult? And the reason being is that you normally work with extremely limited data. And most of the problems that we have in marketing mix modeling come from the fact that we have rather limited data, which we also call the small data problem. So normally, if you're lucky, your clients, your partners that you're working with can give you 2 years worth of data, historical data, that is aggregated on a daily level. So we work with time series models. Sometimes it's aggregated on the weekly level. That's 100 data points or 730 data points. That's definitely not enough for your 70 trillion Claude, whatever model to fit, right? So we have to work with that still. We suffer from contradicting results. We have lack of granularity. We need to aggregate the data to a very high level, all very bad. And so it's a quite challenging problem. And what makes it further challenging is that we actually try to learn very, very many things from very little data. So as I just said, we have 730 rows. Sometimes we have just 104 rows. And we actually try to infer quite a few parameters from this data. So normally we work with saturation. Saturation, if some of you here come from the field of economics, you might have heard of diminishing returns to scale. So as we scale up the investment, we don't get the same return. And that is what we normally believe we have in advertising as well. So when you spend 10,000 euros on Google Ads every month, and you suddenly crank it up to 20,000 euros, it's not going to have the same effect, right? The efficiency, the marginal efficiency is going to decrease. So you need to learn, you need to account in your marketing model for this saturation. You have ad stock. What is ad stock? Ad stock essentially means that advertising that you do today still has an effect tomorrow. It's quite normal, right? Many of you probably remember at least 1 or 2 television ads that they saw a while back. So this is something we also need to account for. Then we also normally dealing with some kind of baseline. So of course, as marketers, we like to believe that all of our sales are driven by advertising, but I can assure you that's not true. So typically we have some kind of base demand. That's also varying over time. So it sounds like a regular intercept you have in your linear regression, but it's also time varying, which makes it even more challenging to model. And then we have coefficients, of course, like all our media data have their coefficients, but these might vary over time as well. So that's even more parameters in our model. And all the data scientists here, they will probably already cringe because we have so many parameters that we try to infer from really what is not a lot, which is actually a very, very tiny amount of data. Now, the good thing here is, though, that we have fixed functional forms. for all these parameters, more or less, right? So we don't know what the exact parameters are, but we know how these functions should look like, which helps us a little bit, as we will see later. Now, this is actually something that quite a few people in the industry are thinking about right now. It's not just us. So somebody a couple of years back came up with a fancy term. It's called triangulation. And those of you who have heard of the term before, they probably heard of it in the context of, you have a couple of cell towers, and then if you have 3 of them, you can kind of pinpoint the location of a phone that's somewhere in between those towers, right? If we have 3, you're fine. And what people try to do conceptually is try to kind of try to bring that concept to marketing measurement. We actually know that you have a couple of methods, and none of these methods is perfect. Actually, all of them are flawed. But the idea, at least, is that once you combine them, you actually kind of can overcome your individual blind spots and approximate or triangulate the truth. And that is also what we're trying to do here at Funnel Measurement. So we're not just doing marketing mix modeling. We're also doing incrementality testing and digital attribution. And we try to inform our marketing mix model by the results of these other methods, which are in and by itself probably also flawed. But when we combine them, the idea is that we can triangulate the truth or approximate the truth. Now, how do we do this? That's what I want to talk about today. And triangulation actually means calibration. At the end of the day, we want to have a way where our marketing mix model, which in itself, as you recall, is a regression model that learns from media input, the relationship to sales output. We want to have a way how we can inform or integrate results from other methods of measuring our marketing in the learning process. And that is essentially what we call calibration. Sounds easy when you draw this on a fancy sales slide, or say a fancy Stockholm AI talk slide like that. But it's actually not. Fortunately, though, other people than myself or my team have thought about that already. So we can at least take a little bit, maybe we can take 1 or 2 pages out of the playbook. And when reviewing the current approaches out there for calibration that currently exist, we can quickly find that there are basically 2 main flavors. So on the one hand side, you can work with Bayesian priors, and on the other hand, you can work with multi-objective optimization. So that sounds a little bit like the classic Bayesian versus frequentist war that we deal with everywhere in data science, since before I even got into data science. But in this case, it really isn't. It's more like it's not as religious, trust me. It's more like just a different approach to things. And Bayesian priors, who of you has dealt with Bayesian statistics before? But how many have? You have, of course, as well. 4. So essentially, what we try to do is we set up a Bayesian model, and we give a prior distribution that kind of regularizes or restricts our coefficient, pushes it, or our parameters, pushes them in the specific direction related to the prior distribution. And if there's support for that in the data, that's good. If the data points in a completely different direction, provided we have enough of it, we would also then move in a different direction. But at least we kind of try to fit the model into that direction a bit. Now, if you work with a simple linear regression model, probably quite easy to derive a prior from some sources of calibration data. In marketing mix modeling, as I showed you earlier, we get a bunch of different parameters and different transformations for the data. So it might not be as obvious anymore, but it can definitely be done. And there are a couple of libraries out there that implement this approach. We have PIMC marketing by the folks who also maintain a lot of the PIMC library. If you've heard of that before, we have Meridian, which is a framework popularized and maintained by Google itself. And on the other hand, we have the multi-objective optimization approach. And that one is popularized by Meta. So essentially, this is a Google versus Meta slide, low-key. So in the multi-objective optimization approach, we essentially treat the marketing mix modeling problem as a hyperparameter optimization problem. So those of you who have dabbled in machine learning a bit before probably have dealt with hyperparameter optimization. You might want to find the perfect number of trees for your random forest, or the perfect tree depth for your gradient boosting machine, or just the right regularization parameter for your ridge regression. What you do is you run a lot of different models, cross-validate, and try a lot of different of these hyperparameters out. Now, if you think about it, you can actually treat everything as a hyperparameter, also transformations of the data. And the parameters that I showed you earlier, those can be represented as transformations to the data as well. So if you want to implement saturation, you can just transform your input data with the saturation function. So the data transformation parameter becomes a hyperparameter in that sense as well. Now, you can obviously do that at scale, run a lot of different models, and where you treat everything as a hyperparameter, but that still won't solve the calibration problem, right? If you just do standard hyperparameter optimization, you always optimize for something, which normally is something like goodness of fit on the training or on the validation side. But when you treat this as a multi-objective problem, then suddenly calibration becomes possible. Because recall what calibration means is that we try to get the model close to some other sources of truth, to some other forms of attribution. And now actually what you can do is you can encode this calibration logic via some distance metrics into your optimization problem. So suddenly you're not just optimizing for root mean squared error or some other machine learning metric, but you're actually getting another secondary objective that describes how well your model fits with the calibration data, which is also some kind of distance metrics. And now you run a lot of different models for a very long time, and you calculate your calibration losses, you calculate your machine learning loss, and hopefully you'll find something that does good on both. And that means you have to run many, many models for a long time. Whereas in the Bayesian approach, you just have to run one model also for a long time. So you can see the defining thread is here, running things for a very long time. But essentially, with both approaches, you're essentially more likely to find a solution that fits in with the calibration data if the training data supports that. If not, you're still not going to find that solution because it doesn't exist. But then at least you're sure that the data really doesn't support it, which is a conclusion in and by itself. And if you think about that, as a data scientist, you would probably have realized by now that this is really just regularization in disguise. What is regularization at the end of the day? We try to add some parameters to the loss function such that we don't only optimize for the loss itself, but also have some satisfy some other requirements. Like for example, in ridge regression, we minimize the squared sum of errors, but we also add squared error term for the size of the coefficient. So essentially, regularization just means we try to kind of do something to the loss function such that we are able to fit it in with some other requirements better. So at the end of the day, calibration is just a very, very fancy, very marketing way of saying regularization, which is cool because then we as data scientists can actually do something with it. Now, I quickly want to drill down on the multi-objective optimization approach, which by now you would have probably realized that that's the approach to the problem that we are taking. And if you think about it, multi-objective optimization is really everywhere, right? It's not quite common that you have just one single objective and you really just optimize for that at all costs. So we have it in finance. Some of you, anyone here with a finance background? All right, so you've probably heard of the modern portfolio theory, the Markowitz approach, where essentially you don't just look for the portfolio with the best return, but you actually want to end up with an efficient frontier of risk-return optimized portfolios. So this Pareto front, the red dashed line, that gives us all the portfolios where for the given level of return, we can't end up with a better level of risk. That's quite normal, right? Because what does it help you really if you have the best possible return ever, but you also have a 99% of chance of losing all your money? Yeah, then you should probably invest in Bitcoin. We of course also have in the marketing measurement, as I mentioned before. Facebook popularized it with the Robin package. But I think most commonly we encounter multi-objective optimization. in life, right? I mean, some of you here are probably juggling different responsibilities, jobs, career, partner, sports, kids, whatever. That's multi-objective optimization in real life. So it's actually quite a fascinating topic, very relevant, and it's surprisingly understudied. So most optimization textbooks in university, they focus on the single objective optimization problem. Of course, it's easier, but it's also way less useful. And so while we were at this, we found that actually there are not so many libraries and so many software programs that actually support this as there are for the single objective case. Now, still, we found one, fortunately. So this is what we're doing. This is how it looks like. We have our marketing mix model that takes into account all our input variables, our media variables, spend, impressions, reach, but also quite a few other sources of data, like non-media control variables, events, price, discounts, place. We can take into account weather, but don't bother so much with the weather. It's not so important. Google Trends, whatever, can take into account a lot of data. And then we fit the model. And the model, as I just mentioned before, it's the machine learning model or the statistical model itself, but it also already accounts for the different transformation we're doing to the data, because we treat data transformations as hyperparameters. Now, we calculate this model with one version of it, randomly chosen version of parameters. And then we calculate our predictions. Now we calculate our attributions as well. And this is where the multi-objective case really comes into play now. Now we can calculate our benchmark KPIs, our other loss functions, our secondary objectives, which sometimes we have a few thereof, sometimes maybe just one, and our machine learning KPIs as well. And then we do this for a lot of iterations. So as I said before, we have to run things for a long time. And then eventually we come up with this Pareto frontier, this Pareto optimal set of models that optimize the trade-off between the benchmark KPIs and the machine learning KPIs. So eventually we can select a model from that and calculate our final attributions. The problem here is whenever you do multi-objective, you never end up with a single result. Now, for those of you who have played in a Kaggle competition before or just optimized the accuracy on the test set for a particular model or a particular data set, you always had that one true north metric, right? Whether that's ROC-AUG score or log loss or whatever, it's one metric. So you know which model is the best. But here, we don't know because we don't end up with one single result. We end up with a Pareto optimal front of results. So we still need to select, which is a bit of a hassle in and by itself as well. So that's that. So at the end of the day, there needs to be a selection procedure as well, because we don't always end up with just one model. That just as a side note, though, how do we achieve this? Which I think was kind of the defining thread of the talk today. And first, let's talk a little bit about what are the key ingredients that we needed to implement first, or that we needed to procure, to search for, so we could get this up and running. First of all, we implemented all the different marketing mix model versions that we're using within marketing mix modeling abstract base class, which is, for those of you who know scikit-learn, essentially just gave us a scikit-learn style fit and predict interface to marketing mix models. That we did, so we could flexibly extend our marketing mix modeling library and just substitute new with old models, new developments, and essentially just plug new marketing mix models as our data scientists develop them inside this optimization routine. Really helpful and really made this project possible in the first place. Then, of course, we needed multi-objective optimization. We didn't want to implement that from scratch because we are all very smart, of course, I hope. But we're also just a very small team, and we definitely don't want to reinvent the wheel. Another requirement we had is that we needed so-called black box optimization, or the fancier term is gradient-free optimization. Because honestly, again, the people on my team are smart, but there's no way they will know the gradient in a guaranteed way for all of these models we're implementing with all of these different complex convoluted set of parameters. So we essentially just needed something that we could plug in and essentially work with this kind of ask and tell interface. We give it data, it gives back a prediction. And with that prediction, we can calculate the loss function. So we needed the black box or gradient-free, fancy word, gradient-free optimization routine. And of course, we needed to satisfy the multi-objective requirement as I have explained at length by now. And then I think I mentioned before this takes a long time, right? Did I? Yeah, cool. So we needed scalable parallelization, but we also needed intelligent parallelization. Because learning, if you think about it, no matter how much we talk about parallelization, but at the end of the day, learning is sequential. You do something, you achieve a result, you check how good it is, you try the next thing. But it is that is always sequential in a way. You can parallelize it a bit, but you need to parallelize it in a smart way, otherwise you're not going to learn anything. And again, something that honestly sounds quite difficult to do. So maybe we can find a partner or a software framework who could help us out with that. And lastly, I mean, this was back when we didn't even belong to Funnel. So the company I worked for got acquired last year by Funnel. We're a small startup. So one thing we could definitely not waste money on was idling resources. So we needed auto-scaling and proper, smart, well-implemented auto-scaling that actually works. So those were the requirements or the key ingredients. So then we set out to search for a partner and a framework that could actually help us accomplish that. So we actually chose Anyscale, and as a software, it's an open source framework actually, as a software framework, we chose Ray. And Anyscale is the company that offers a managed service on top of that, and they are trusted by OpenAI. Yeah, very cool. Main requirement, basically, fulfilled. So actually, so what is Anyscale? What is Ray? Ray essentially is a Python framework for parallel computing that, and I think the main and most popular component here is RayTune, which essentially is a very good and very popular framework for parallel hyperparameter optimization. So it's hugely popular with the AI and machine learning crowd, even before ChatGPT, quite popular. And the good thing, as I said before, like we don't want to reinvent the wheel. So it offers out-of-the-box plug-and-play support for many popular optimization algorithms and training libraries. And the good thing, the additional good thing, some of them are even multi-objective, which is great. And now that is open source. Ray is open source. So we could just implement this ourselves, right? But we still chose to work with Anyscale. And so what is Anyscale? Anyscale is a company that just maintains Ray. So most of the Ray developers work at Anyscale. Turns out you actually need a day job. You cannot just do open source work every day. Actually need a salary. Anyscale provides that, which is great. And it's amazing that you actually, those people are really smart and you actually get access to them if you work together with them. So that's great as well. And what they actually offer is they offer managed service on top of Ray. And that's quite convenient because you get a lot of management console, support, governance, all of that you need as a company running these things. And it can actually also run in most clouds. So we could just plug this into our AWS and it worked. Well, after like 3 or 4 months, something like that. And what we really like about them is they provide a rather, seamless workflow, developer workflow to go from concept to production quite quickly. So this whole thing, actually, that I showed here, how long do you think it took us to implement? Yeah, so it took about 3 months. And I think if we had to implement everything from scratch, probably we wouldn't be done by now. So that was quite convenient. And that's why we love to work with them. When we worked with them before, it was cool. See, that blog post is from 2022. That's way before OpenAI even was a thing. Or maybe not before they were a thing, but definitely before ChatGPT was a thing. Great people also. So why did we implement this from scratch with open source Ray? And there's one simple reason for that. Marketing mix modeling is already hard enough. Machine learning ops is also really hard. And we have to choose our hard with the limited team that we have. Now, how does this look in practice? This is essentially our model building interface, where you can select how all the variables influence each other, which variables go into the model, basically an abstract representation of your marketing mix model. And then this is the interface we provide essentially for our users or our internal customers, our measurement consultants, and even some customers themselves to the Anyscale platform that runs in the background. You can trigger one of these runs that I depicted earlier. And what I highlighted here is the multi-objective part. So here you can actually select the different loss functions that go into the optimization. Now, I think in the LinkedIn post to this talk, there was something about how to go from weeks to hours So who thinks we actually ever ran this for a couple of weeks? Yeah, no one, right? Also, no one believes in Santa Claus, so that's great. And the reason why I brought this up is that normally this would take weeks if you run it sequentially, but then you just wouldn't do it. So you don't just make things faster, you just enable them in the first place with intelligent and smart parallelization like this, which is great. So yeah, that was basically it. That's the team behind, data science team at Funnel, based in Hamburg. Maybe at some point we have positions in Stockholm as well. And yeah, thank you very much. Any questions, let me know. Yes, please. Yeah, we have too many normally. So people throw in things that they still want to account for. And then then what that does is, that's probably why you're asking, that explodes the decision surface, so to say, because some things might do better on one task, the other things might work better on another. So I'm always going on about, like, honestly, don't do more than 3, but people do more than 3. Yeah. Short answer is we don't really. I think most people in the community are quite open about sharing what they're doing. So Meta has published Robin, Google has published Meridian. They might also have some commercial interest in that. That is clear. But we also, as a company, and I think Funnel is also very strong in that, we aim to be rather more transparent than super protective, and we think that will serve us in the long run. That may change eventually, but as of now, this is out in the open. This talk is public, so if anyone wants to implement that, be my guest. It's definitely not easy. So, yeah, Bruno. Cool. Any other question? Yeah, great question. That's probably the reason we are part of Funnel. So we started out as a company in 2016, the Attribution company where I used to work before, and then we became a Funnel customer in 2019 to solve the clean data problem. And that has turned out really well, so well that I'm standing here now and holding presentations in the Funnel CI. Now that is for the ad platform data. I think we're doing pretty well as a company to, just get automated, clean. I think we call that business ready data from the ad platforms. But then, of course, marketing mix modeling is not only about ad platform data, and there you will always have some kind of client supply data, and that's where the fun starts. We work with templates, we work with schemas, we send them example files, and that works quite well. I mean, our customers are also quite smart, but you always have the odd, as a data scientist, you just have different expectations to the data than somebody else. Yeah. Cool. All right. So then I have the pleasure to, well, first reintroduce Armin, who's gonna take over after me. And do we have a break, Makeda? Yeah, we have a.
You want to have a break? 5 minutes only. We can have more if you want to get more food or drinks. You are more than welcome. You know where to find toilets close to the entrance. And let's welcome you back in 10 minutes. He gives you 10 minutes. Thank you. do slideshow. Started to, or just full screen. I
Ah, beautiful.
think the slideshow does that. No,
Yeah, that's fine.
is it fine?
I think so. I think it's all right.
All right. You need anything else? You have your drink?
No, everything is fine. Thank you so much. Okay, I think we're gonna start with the next one. And actually, it's me, so it's really weird, very strange. You know. Yeah. So normally I just present people here, and they do their magic. So I'll just talk a little bit about what I've done, and it's actually done with a colleague of mine or an ex-colleague of mine and a good friend of mine. So I'll introduce him in a second, but hopefully he's in London today. Otherwise, he probably would have presented this with me. So I hope that he's that I do him proud. You know? So my name is Armin. I'm like I said before, head of AI at Aloi and a vice chair of Stockholm AI. And this is actually probably the funnest or coolest project I did last year. It's all right, no problem. So it was actually a competition, a statistics competition that we did as part of Eurostat, which is tied to European Commission or EU Commission. And it's pretty cool. I don't know if you know about Eurostat, but you should check them out. I mean, we had a chat before with Martin about the maybe ways that they present the data, which is maybe sometimes questionable in terms of PR, but it's a great resource just to kind of train your statistical muscle. Tim, yeah, I mean, you probably have seen this meme here. You know, you throw in a bunch of data, you get some results, you stir it a little bit more, then you get better results, and that's machine learning. But that's probably how it shouldn't be. So, and I'm putting it here because that's not how you should do stuff. You should do how Tim does it, which is, you know, properly. So, you know, as part of the competition, we had to put a title or a name, sorry, to our team, and we called ourselves Team Title. So we wanted to be called Untitled, but we thought that was too boring. So Team Title, and it was Drew and me, and so Drew is a senior data scientist at Codon. So combined, we've been you know, doing this for about 25 years, I think. And we worked across a number of companies. So we were colleagues at EQT in the Motherbrain, which was the AI team there. We also worked at Ericsson, Spotify, Amazon, and Schibsted as well. And also in different countries, in US, UK, Sweden, and Luxembourg. So a little background on what this is all about. So it was a competition called a classification challenge. And I'm putting all the references here for you so you can have a look later on because it's a lot of cool stuff here. By Eurostat. And so we talk a lot of crap about EU and Europe, but Eurostat is what it does have is it's got a lot of good data sets, and they're always up to date, and they're usually pretty clean. So if you just want to go play around with some really nice real world data, just go to Eurostat. You can find everything from like economics data, imports, exports, marketing data, all kinds of stuff. So the problem that we faced with was that you have job advertisement, and we had 33,000 samples of job advertisements, and each advertisement has an ID, it has a title, and it has a description, and you're supposed to assign a 4-digit occupation ID. So you're supposed to say what kind of occupation this basically is. Now we had some restrictions, which is that you cannot use third-party APIs, so you can't use ChatGPT. That's not allowed. Yeah, there you go. Boom. So you actually had to sign an NDA to get this data set, which was kind of funny. So you have to sign an NDA. In the NDA, I work with law now. So now I'm like very attuned to clauses and things in legal documents, but back then I wasn't. But we actually spotted like a lot of different things when we emailed them about it, and it took them a couple of weeks to respond. But yeah, you cannot use APIs. Also, there was no labels or ground truth given at all. So this is what you would say in machine learning and unsupervised learning task. And you're only given 10 tries. So you do your predictions and you upload it to this website, and then it gives you the results, and you can only do that 10 times. So a few constraints there. And spoiler, we finished 5th. We didn't win. The prize was about 25,000 euros if you won. So it's not too bad. And you have about 2 or 3 of these competitions a year. So if you do like little consulting on the side, and then you do a couple of these competitions, you can make some money out of this. It's no problem. But so I put this. So I'll talk about the metric that was used. But we're about this LCO 0.02 from the top spot, meaning that I think from the second spot, honestly, if we just changed the random seed, probably we would have taken it. So that's how close the competition was. And it also tells you a bit about the limitation of this data set that you worked with. So first we need to dig into like what is all this stuff about occupations, and we learned a lot about ISCO ontologies. So ISCO I think stands for International Standard for Classifying Occupations, and it's developed by something called an ILO, International Labor Organization, which was established in 1918 by the League of Nations, so before the UN. And so what they do is they publish things related to a labor market and jobs. And the first ISCO standard was 58, so 1958. The second one was 1988, and the third one is 08, so meaning 2008. So probably the next one is probably going to come out in the next 2 or 3 years because they need to update some jobs. And what it is, it's an ontology, and you have it's like a 4-level tree structure. So for every occupation, you have a four-digit code. So I've given here something called generalist medical practitioner, which is like if you go to, I guess, Kri or Vård Central here in Stockholm, that's who you deal with, generalist medical practitioner. And you have like the top level, the root level is 2, meaning it's a professional. Then the second level is 2.2, health professional. Then 2.1, medical doctor, and then you get to the bottom there. So our job was to assign this 4-digit code to a job ad, basically. And the reason why that's useful is because the European Commission does a lot of work in trying to analyze what the trends are, what the job markets look like across different countries, just to kind of basically create budgets and sort of do estimates for the coming, let's say, 5 years. So it's kind of a useful task to them. What they do now, I suppose, is they get a lot of interns to kind of do this sort of stuff, which is not that great. So in machine learning tasks, you usually start with, you get the data, you start exploring the data. I'll talk about that in a second, but you start from evaluations. You have to define, what you're trying to optimize for and how do you evaluate that, right? And usually, kind of in a general sense, people talk about accuracy, which is not a very good metric most of the time. Usually there's something else, precision, recall, F1 score, or the metrics that Tim talked about. In this case, we talk about a metric called LCA, which is lowest common ancestor or least common ancestor, which is coming from the graph theory. So the way you evaluate this is you basically, if you can see, you have the 2 bottom green nodes there, and JOK, which is to your left, that's the one that I'm predicting. And the one to your right is the one that's actually the ground truth. And you're trying to estimate at what level is the nearest ancestor of these 2, basically. And ideally, if they always have the ancestor that's the immediate ancestor, basically, you're going to have a score that's close to 1 or 1, basically. And if you are mispredicting completely, then you're going to be close to 0. So it's a score between 0 and 1. So no accuracy or anything. It's more LCA. And again, we don't have ground truth. So whatever we do, we have no idea how it performs. There's no way for us to verify. The job ad data itself, so these are the actual job advertisements, they were mostly English, and then the rest was kind of fairly uniformly distributed. German was probably the second most common language, but surprisingly, for example, Bulgarian was the third most common. So a lot of these languages are kind of fairly uniform, and English is at the very top. And there's some like Japanese and Catalan and Serbian at the tail end there. And also kind of looking at sort of the word distribution or the token distribution of these ads, you notice that some of them are very short, not very informative, and others are just like, you can tell that they were just scraped from websites like LinkedIn and Glassdoor, because you just have a whole bunch of HTML stuff in there and not a lot of context, you know. So not a superbly high quality data set to begin with. And then we try to kind of do some, we did some rules, we created some rules to match very top level, like L1, you know, the very top highest level ISCO ontology, to map that and see how the volume of these ads were distributed across different occupations. And it was predominantly professionals, so professionals, managers, technicians, and those kind of professions, but also a few others, like there was trade workers and craftsmen and craftswomen and elementary occupations as well. So it was a little bit of everything. It wasn't just like engineers, basically. So what do you do with this stuff? So the first thing we did was we tried to figure out, how do we make this data set even better? And that's one important lesson, like you try to enrich your data or fuse it with something else. So we did some research and found something called European Skills, Competencies and Occupations, or ESCO, which is another ontology which maps to the other one, the ISCO one, right? But what it does is it gives you another level now. So it gives you now 5th level, which just makes, you know, just makes the mapping much better. Like it gives you more fine-grained sort of a mapping. So you can't maybe see it from there, but the bottom purple one is livestock and dairy producers. And ESCO provides additional kind of occupations called pig breeder, horse breeder, cattle breeder, and equine yard manager. So we decided to use the ESCO one actually, because it gives you more granularity, and it maps to the ISCO one. So that's a lesson. Try to find even better data. The actual ontologies themselves, like what they were constructed of, was you had occupation title, you had this level and the code, you had a description, you had some tasks and responsibilities, you had like common advertised job titles that are out there, and it was in all languages. So you had it in Chinese, you had it in Greek, you had it in Italian, so exactly the same information kind of duplicated in different languages. Then we noticed that there was some things in there in the description called some related occupations classified elsewhere. And we actually, when we were doing our building our models, we found that that was actually polluting our model. So we put a regex, or we put a rule in there to actually remove that, and things were much better. So that was nice. So how do we solve this? So we did a first solution, very first solution, called fuzzy title matching. So not very glamorous, but we basically literally just looking at the titles and trying to map it directly to the title of the ontology, with some leeway. Basically, that's why it's fuzzy. So you can account for some differences there. So we found that a lot of them were actually direct matches, but unfortunately, the job advertisements are usually more kind of nuanced, right? So if you have a title engineer, what does that mean exactly? What kind of an engineer are you, right? So you really need to look in the description. But we thought, hey, let's start off with this, because this gives us a very simple baseline that we can run very quickly, and then everything else should be much better than this, right? So he gave us this LCA score 0.35. And then went to the second solution. Again, like go a little bit more up in complexity. So we decided to do something called K nearest neighbors, very classic lazy learner method. So you're not actually technically training any models. You can optimize for the thresholds at the KNN, you know, where you separate the boundaries, but you know, there is no model parameters or anything like that in here. So what we did was we embed the titles, sorry, the occupations, so the descriptions, and also the job ads. And then we do a nearest neighbor lookup using something called cosine distance, and then we get the top one, basically. But before we do that, we actually found that the data sets were very asymmetrical. So what you want to do is you want them to have them as similar to each other as possible, meaning that you know, you don't want to have very short text versus very long text matching. That's not usually optimal. So we did some transformations there. So we actually created like a data pre-processing task where we use an LLM to extract certain bits from both occupations and from job ads. And we use the local llama because remember, we can't use ChatGPT. We can't use APIs. So we just ran a llama on a computer similar to this one, a MacBook, overnight. And it did two things. One was translated everything to English first because we wanted to stick to just English to simplify things. And two, it extracted all this information. And then we embedded it using something called the Stella. It's a Chinese-built model, a very small one, 400 million parameters, small. And then we did this just a cosine similarity with each other, and then just took the top one. And then we got a score of 0.48. So we're happy, 0.35 to 0.48. That's great. At this point, we were third in the leaderboard, you know. So this was just an example. So this is what the job ad looks like. So it's got a lot of stuff. It's like location, Brussels, Belgium, about us, position overview, key responsibilities, etc. So we convert that into this, a JSON, and then we embed the JSON itself. And then we do exactly the same thing with the ontologies, and then we embed the JSON from ontologies as well. So they're very symmetrical then, very easy to compare. So the third solution, at the time, I don't know if you know this, but like from around autumn 2023 till autumn last year, there's all these influencers online, you know, talking about synthetic data. Like we should use synthetic data, you know, that's the future. So Drew and I thought, hey, let's try synthetic data. So what we did was we took the ontologies and we actually used the Open AI because there was no NDA on these ontologies. You can just download them from the internet. Anyone can do it. So we sent them to GPT-4o and we generated fake job ads, 160,000 of them. Very balanced across all the different occupations. It's perfect. It's machine learning dream, balanced data set, you know, balanced classes. Spent about 200 euros. I'm like, it's all right. We'll win 20,000 euros. It's no problem. And then it just becomes a classic supervised learning task, right? You take a nice BERT-based embedding model. You had a whole bunch of layers to it, dropouts, regularization. You had a softmax head to it, and it's wonderful, you know. And we're training it all, and we're looking at the training loss, and starts to look fishy, you know. Starts to look a little bit questionable. It looks too perfect. Everything looks too perfect. And then we submitted our results, and we get the same score as the previous method, basically. So all this money spent and all this effort to kind of synthesize all these job ads, and no, not good. So we're very angry. But then we did some analysis and we found that, first of all, the LLM couldn't match the shittiness of the job ads. The job ads are so crappy that, you know, it tries to be too perfect. And the second thing is that the diversity was not there. So, you know, if you think about it, like the LLM is basically like one person that's just generating all these different ads, but the ads are generating by completely different entities that have a whole different story behind it when it comes to generating data. So it was just too uniform, effectively. And we try to force it to be a bit different, but you just couldn't. So this didn't work. So then we went with the fourth solution. We're like, okay, let's go back to our Canaan. That's a promising start, simple start. So what do? We just added some re-ranking on top of it. So you take your nearest neighbors, and then we did a two-step re-ranking. One was a rule-based one. So I invented two rules called winner takes all and relative placement. So essentially, we look at the top 5 cosine similarity or cosine distances. And then we do some re-ranking on that using these two rules. And usually it's a hit, like we get a winner from those. And then the ones that are not a winner, or it's basically ambiguous who the winner is, which occupation it is, we basically send it back to the Llama LLM to do the re-ranking for us. So we tell the LLM to, okay, please pick the one that's best match for this. And yeah, we got a score of 0.55. So that took us, I think, in a second spot at that stage. We got bumped out to the 5th eventually. So, you know, but that was really nice. So this is, that was, I think, on our 10th try. So we're done by that stage and we're just like, come on, please. But this is what the architecture looked like in the end. So basically, we had on the one hand, we had the titles and descriptions of the job ads. So we would do translation to English. We would do this extraction of the title, description, and skills. Then we have something called a query, and we embed that query. And then on the other side, we have these taxonomies where we have the ISCO taxonomy. We enrich it with the ESCO taxonomy. We do some cleanup there, similar to the one that we did on the job ads. And then we just use that as a reference to match against. And then you have the embedding, neighbor lookup, and re-ranking, and then the final prediction. So that's the flow. And the whole thing ran just on your MacBook, basically. So anyone that has any decent computer or laptop can just run this, no problem at all. But a funny story. So when I was doing the translations for the synthetic data set, I left the laptop in the kitchen, so it's running overnight. So I went to the bedroom, and then my wife, she woke up at like 2 a.m. or something, had to go to the toilet, and she's passing by the kitchen, and then she sees this thing going. So she just comes over and she just puts the lid down. And that was that. And then Drew was like, in the morning, he's messaging on WhatsApp. Is like, is it ready? Is it ready? I can't wait to, try it out. Sorry, mate. I have to tonight, I promise. So then I put a sign on it, actually. It's like, don't touch. So that worked. Yeah. Yep. And then, a note on prompting. So we use the Llama model, and I don't like this whole prompting thing. It's makes me very uneasy. So I built like a little compiler for it, a prompting compiler. So at that time, the first reasoning models came out, this O1 preview, if you remember that one from OpenAI. So what I do is I pass a one-sentence instruction to O1 and tell it, please give me a chain of thought prompt for Llama. And it actually generates this prompt for me. Then in order for it to be compatible with Llama, I have to do some alignment. There's like certain tokens I need to insert and things like that. So I do that. And then I have my prompt and I give it to the Llama. And then it works beautifully. So you don't have to think about prompting or writing, very complicated instructions. Just one instruction is enough. So that worked really well. So this was the hardware software. Like I said, just a MacBook Pro. Use this MLX LM library. So MLX is Apple Silicon or Apple's own developed machine learning framework, which is customized or optimized, for the ARM processors that are in these notebooks. And then Llama 3.1, 8 billion parameter. It was 8-bit quantized, and Stellar, the Chinese built embedding model. So everything is basically open source, I think. So fully open source. And like I said, we did 10 tries. I showed you 4, but we did 10 tries. And, we tried a lot of other things. Like we tried re-ranking with, TF-IDF methods, if you know NLP, like classic NLP, TF-IDF. I added all kinds of rules for re-ranking as well, like 50 different rules. It was terrible. We tried also reuse the synthetic data. We're like, wait, we spent 200 euros. Let's try to reuse that. So we used that as part of the KNN as well. But that didn't work too well. I guess it was polluting it too much. So we tried a lot of different things. So you just need more time. In machine learning, everything's about time. I mean, Tim mentioned it takes a long time, but it's all about time. You can think of 100 different experiments, but you got 24 hours in a day, right? So it's just that's how it is. So lessons learned and future work. Well, there will be no future work, that's for sure. But lessons learned, right? We did talk about it. Like we still sometimes when we catch up for a beer, we're like, Armin, we should have done that. I'm like, yeah, I know. But exciting. So yeah, always look for ways to just extend your data. Like you have your data set, and everything you do is limited by. Mute the gentleman that's joined. I didn't know you could join this one. Oh wow! So were there people online here? Oh wow! I feel so exposed. There you go. Nice, cool. Yeah. So yeah, lessons learned. try to enrich your data if you can. You'll always, anything that you add on top of it will probably give you some benefit. Start simple. So simple like just heuristics, K and AND, these like classic methods. I mean, they're great. Most of the time they're great. Usually a simple baseline is the one that actually gives you the best results. Re-ranking strategies are always good. Like I've seen that even those ones that I tried but didn't perform so well, they still perform better than not re-ranking. So re-ranking is great. And then synthetic data, you have to. I think you have to like spend. You can't just synthesize data. I think that's an art and a science in itself. I think you have to know exactly what you're doing and how to do it. Saying that though, if you just want to test things out, so you want to build a model and just like try it out on something and have very limited data, it could be worth maybe synthesizing data just for that, just as like a sanity check, basically. And yeah, areas of improvement. This is like beer conversations that Drew and I have. We could have extracted more things from the job ads, like seniority levels and maybe industry categorization that could have maybe given us a little bit better separation between different occupations. We also tune the neighbor search. So we just kind of eyeballed the separation. We like picked the threshold 0.56 or whatever it was. So we could have actually done proper optimization on that. We could have generated like small knowledge graphs that we could incorporate into the embeddings and maybe even in re-ranking. And also, yeah, parallelized workloads, like Tim mentioned it as well. Parallelization is very important. So my laptop was running overnight, but probably if I spent, a day thinking of it more from engineering and scaling perspective, I could have, gotten that much better. So those were and yeah, if you want, you can clone this repo and you can just run it. You don't have the data because you don't have the NDA, but we do have. I think I provided some samples in there. I was naughty. So thank you. Any questions? Yeah. Yes. Yeah, June last year till September last year. Yes. Yeah. We haven't. So that was one thing that we did think about, like basically just renting bigger, like a cluster, and then just instantiating like a much larger model. And no, we haven't tried it. So maybe that's why the other guys won. Who knows? They had a bigger model, but that's a good point. Yeah. Yes. Make it. Yeah, exactly. I don't have a lot of money, but yeah. Ah. Okay. Okay. Cool. Yeah. Nice. Mm. Mm. Yeah. So I have a theory based on the scoring in the competition, because like the top like 5, 6, maybe the couple of ones below us as well, it was so close to score, and given how crappy the data was, I feel like maybe we were getting close to the kind of the limit actually of that data set, basically. So even if you had maybe a bigger model, just the fact that the data was like that, you couldn't like squeeze anything more out of it. Because so again, second theory is that when you send this data set and gets scored, it gets scored against some ground truth that's behind the scenes. You don't know what that is. And my second theory is that there was just a bunch of interns labeling that ground truth. So probably the ground truth itself is questionable to begin with. But yes, bigger model, probably, I don't know, maybe. Yes. Yes. Martin. Yeah. No. I think they still haven't actually. I don't think they still haven't the results, official results yet. but we're like, we lost. It's all right. You know, we'll take it. It's no problem. Yes. Yes. Yeah, we did that. Sorry, I should have mentioned that. We did that. So we would, from each one, we would look at, so that was the basis for us to decide. We did actually a lot more experiments. We probably did about 30 experiments, 10 tries. So what we do is look at the overlap of the current one with the previous one. Yes, we did. And also to see how the ones that were very different, we would just eyeball them. But like to me, everything looked good. You know, that's the thing. Like I'm looking at this, I'm like, yeah, this is a nurse. Surely this is a nurse. But no, it's not. You know. Well, I don't know. Yeah. So yes, Reza, you had a. Yeah. Yes. For the ontologies. So not for the data, for the job ad data. And I think the reason for that, if I remember from the NDA, is it's EU, you know, so it's you know, GDPR. So and when you actually look through the data when you're reading it, there are a lot of like names and things in there. So I think that's why. But the ontologies you can send, no problem. Yeah. Yes. Any other questions? Yeah. Yeah, I mean, if you so the reason actually why Drew and I joined this competition is because we did something kind of similar at our previous job. So that's an investment company, and what they basically try to look for is, you know, like first of all, looking at in general where different positions or different occupations are growing. So they can kind of zero in a particular sector and see what's going on there. So if there is a lot of, I mean, it's kind of obvious, right? But if there's like a lot of data scientists and machine learning engineers, then probably AI and machine learning is ripe, right? But also because that particular company that we work for, they were collecting a lot of data from different data providers. It was basically, I think, 500 million data points on basically different people and where they worked. So they would categorize the data on like what kind of occupations these people had, and we would develop effectively flow graphs or funnel diagrams, where you would see, for example, a company that maybe we're interested in. You can see where and what kind of occupations are coming in and what kind of occupations are going out. And that gives you all kinds of signals. They can see maybe they are scaling down their R&D. Maybe they're now increasing in their commercial aspects like marketing and sales. And that's a pretty good signal that you can use then to maybe, okay, they're maybe getting for a big commercial launch. Maybe we should start talking to them, start off making some offers, you know. So it does have like also private commercial applications, yes. So we were very unsuccessful when we did that, because there was no large language models at the time when we were doing that. So we did everything like we trained our own models using classic NLP methods. But now it's a bit easier. Yeah. Cool. Thank you so much. Thank you.
Thank you, Armin. Do you have any meetup coming up that you would like to invite people to?
The next one is in. Sorry. The next one is in September, I believe, right? And that's actually Carolyn. There she is. So it's a big one with Ericsson, and Carolyn is actually helping organize that from Ericsson's side, and Mistral, who are flying in from Paris. So Mistral will be coming for the second time again to Stockholm, and I think this time we aim to bring Mistral researchers here, because it's going to be Ericsson researchers as well. So the last one was a little bit more kind of a go-to-market sort of a presentation, but this one should be very kind of engineering and research hardcore. So that's, I think, 4th of September, right? And we might have something before that, and we have a whole bunch of them lined up afterwards with Microsoft, medical, AI. I talked to Martin before, he's interested, so we talked to him. So we do have quite a few. But become a member, and you'll find all about this basically. So.
Thank you. Thank you for coming. You are welcome to mingle and take more food and drinks if you want to. And ice cream. Yes, please eat ice cream. Yeah, help yourself. It's over there with the blue sign. And we need to empty the office before 8:30, correct, Dani? So 8:30, 2020 or 2030 latest, because then the cleaning crew is coming and we want to give them space to clean the office. But you are more than welcome to talk to your newly acquired friends and old friends. And thank you for coming to Funnel.